Welcome to Finite Element Analysis tutorial. We'll be learning about composite overwrapped pressure vessel. There's another video you can watch that goes into the extensive details of these kinds of analysis. But composite overwrapped pressure vessels provide a opportunity to save weight in designs. And what they do is they use a composite wrap, which is high strength fiber materials. And you can see an example here. You have a filament wound composite with an inner metal barrier. And that liner, we call it liner, is a barrier so that leak does not occur through the wall. And why we need that is because the composite is porous and is a matrix material, and at high pressure you're going to have permeation through the wall, and so the liner acts like a barrier. And that typical liner material can be rubber, plastic, metal. If it's metal, typically it's done so it's thin and ductile. And the purpose there is so that I'll explain a little bit later, but what we want to do is increase the pressure in such a manner that that liner goes into plasticity. And the idea is that when you release the pressure load, that the liner then becomes in compression. And so when you load it up the next time, now the liner will be partially in tension, and so it will be actually more durable to cyclic loading. These Countdown COPVs are used quite a bit in the industry, spacecraft, launch vehicles, aircraft. And you can see here in this example is bonded, but there could be examples where this liner is not bonded to the composite. That's another application. These have significant weight advantage. If I were to make all this metal, it would be a lot more weight, and more, a lot more weight, and that's the benefit of COPVs here. So, what is analysis methodology, and what are the steps? Typically, what we have here is we will have input data for the composite overwrap pressure vessel, geometric data, winding pattern, and composite data. All this stuff goes into an Abaqus input deck, and you want to run three kinds of cases. So you have usually an auto frottage, which is the opportunity you have now to take that composite overwrap pressure vessel, pressurize it in such a manner that you induce plasticity into the liner. We call that auto frottage. We do that on purpose. So let me explain it. So when the liner is pressurized with the composite and the liner are both resisting the pressure. But when you pressurize it to a level where you plastically deform the liner, what happens is that now the liner wants to stay where it is. And if you release the pressure, the composite wants to push back that it wants to push back the liner back where it was, but it can't because the liner has plastically deformed. So for that reason, then the liner will go into compression. In the subsequent loading condition, you will have a proof test to make sure the workmanship of the overwrap is verified, and then you'll go into your operational cycles, the MEOPs. Typical design burst factors are 1.5 MEOP, maximum expected operating pressure. It could be higher depending upon whether you're looking at Department of Transportation COPV, or you're looking at a NASA COPV. They can range from 2 to 3, these factors. But the important thing is that your analysis models have the ability to do a recovery of ply by ply stresses. So you can look at the stresses and the strains in each ply. So typically, some models include every single ply. Some other models will look at a shell model, which we'll be showing very soon and shortly. The ply angle could vary across the dome. We're going to be focusing on the straight cylinder section, but these dome sections tend to be quite complex to model because the angles and thickness are varying as you move along the dome. And here you can see an example of a COPV model generation. Usually you're going to have the liner contour provided, and then the composite overwrap pressure vessel is based upon the filament wind pattern. That model depends on the wind pattern. The thickness and wrap angle calculation are based on that wind pattern, typically, winding pattern. You can see here again the cylinder section, focus there. And the multi-step analysis will help you go through the sizing, proof, and operation. The liner material, if it's metal, you will have a nonlinear stress strain curve because you may have to include the effects of plasticity to account for the autofretage cycle. Again, the autofretage cycle is done on purpose to make the liner plastic so that it goes into compression. So in subsequent cycles, you're not stressing it as much. In the example we're going to be showing very shortly, I'm going to demonstrate for you the ability to model this in Abaqus. I'm going to pass it along to Lifu Wang.
Thank you, Professor Goyao. And hi, everyone. My name is Li Fu Wang, and today we're going to learn how to use Abaqus GUI settings to analyze a composite pressure vessel problem. So we are going to have two problems today. The first one is designing the composite layout for thin wall pressure vessel. So this is a structure we are going to analyze here. First, we have a quarter of the pressure vessel, and that's why we need to have X symmetry and Z symmetry here. And then we need to have Y symmetry on the left hand side, and on the right hand side we need to have a constraint since we want the pressure vessel to have an elongation in Y direction, but we don't want it to have other non-symmetric degrees of freedom. That's why it's not fully Y symmetry. The radius for the vessel is 10 inches, and the length we just simulate 10 inches. It can be any length. And here is the composite material property. This is a typical laminate property. And then for the layout, we have 30 apply of 30 degrees, minus 30 degrees, 90 and 90. Recall that for thin wall pressure, the longitudinal stress is way smaller than the transverse stress. That's why we need to 90 degrees here to prevent the hoop stress. And the thickness for each layer is 0.009 inches. And according to the experimental result, the failure happens when the longitudinal stress, which means your fiber direction is, longitudinal strain in your fiber direction is greater or equals than 1.5%. So we need to design the layout until your fiber direction strain is smaller than 1.5%. And the stress loading here is the inner pressure should be 6,000 psi. And if you recall the thin wall pressure, sealed thin wall pressure vessel formulas, you should have longitudinal stress equals to PR over T, while your hoop stress equals to PR over T. Sorry, longitudinal stress is PR over 2T. And because shell edge loading is force per unit length, so we need to multiply by the thickness here. According to the formula, it should be PR over 2. Well, we can do a quick test for this kind of loading by entering the pressure equals to 1 psi. So according to the calculation, the T should be 5 times P, which is 5 pounds per inches. And the thickness, let's assume, is 0.1. So according to theoretical calculation, your longitudinal stress should be 50 psi and your hoop stress is 100 psi. If we do this loading, use shell edge loading, and we obtain something close to this theoretical result, then we can say that this kind of loading can perfectly simulate the thin wall pressure pressure loading. So after that, we're going to do the composite layout design. So let's start with Abaqus, building the model. Create a model. Before we start, always remember to set your working directory to the directory you want. So first we create a part. Let's call it quarter shell. It should be a 3D deformable shell, and we use revolution so that it's easier to create. Can make it larger. So we draw a line here. The line rotates for 90 degrees. That will become your quarter shell. So this line, if you go back here, the radius should be 10 inches and the length should be also 10 inches. That means radius 10 inches. This is the axis of symmetry. So radius of 10 inches, we need to start from x equals to 10, and length is 10 inches. That means we draw a vertical line that is 10 inches long. We can choose -5 here, and the ending point is 10, 5. So this length of the line is 10 inches. Rotate 90 degrees and you will get your shell. Notice that the axis of symmetry is in y direction. And then in the property, we define an aluminum first. Aluminum, you should have elastic property 10 mega psi and Poisson's ratio 0.33. So we do composite later. First, we are going to test whether this loading condition is the same as theoretical prediction. So we do a composite layout manager here that will save our time later when we change it to composite. So initially, we only need one of that. So we can delete this plies. And the first ply we call it aluminum. Choose the region by double-clicking it. Material, double-click it and choose aluminum. And thickness, as we written here, it should be 0.1 inches. System layout originally is 0 degree, so we can choose 0 degree. Notice that here the reference axis, which means your one direction axis, is in the hoof stress direction. But we want the reference direction to be the longitudinal direction. So we can use normal direction axis 1 here. Now it moved to this direction. Integration point 3 point. And now we can do assembling. Create assembling, independent assembling. And then following the procedure, you can create your step. It should be a static step. Let's call it loading. So we don't need to change anything here. The thing you need to remember is in the field output. Originally, it has this selected, but to save the simulation time, we can unselect everything. Now we only need a stress, and then we need a total strain. And let's include the plastic strain because we are going to use it later. And if you want, you can include displacement, but it's not necessary. So that's all we need. And don't forget here, we need to output the section point. So this section points, if you still remember, we have 3 integration points per layer. And This 3 represent the top, the middle, mid plane, the top plane, and the bottom plane for each layer. And we only focus on the mid plane for each layer, which means we focus on the second integration point for that. Later, this is only for one layer. If you have 2 layers, then you also probably want the fifth layer, fifth integration point, which means 2 plus 3. And also, if you have 3 layers, then you have 2, 5, 8, another plus 3. Now keep doing that. You should have 11, 14, 17, 20, and keep moving on. Well, right now we only have 1 layer, so only 2 is available here. But we can enter how many layers we want. So let's do 23. Okay. Now, always remember to check this box. You need to include the local coordinate direction. So it will help us a lot later when we try to output the fiber direction string. And then we do the loading. First, we need to set up the boundary condition following this thing. So we need to have X symmetry and Z symmetry. So the boundary condition should be set in the initial. So first is X symmetry. X symmetry is to be applied on the edge that is perpendicular to X axis, which is this one. We don't need to create sets. So apply X symmetry, then create a Z symmetry. It should be applied to the plane that is perpendicular to Z axis, which is this line. So Z symmetry. Also, we need a Y symmetry here on this end, on this edge. So create the Y symmetry. So be applied here. And then we need to apply the special semi-Y symmetry on the right hand side. So if you see what is Y symmetry, you see that Y symmetry, you constrain the degrees of freedom of U2, UR1, and UR3. But now we wanted to have U2 deformation. So this constraint should have, go to displacement here, choose this end, and you only need to fix UR1 and UR3. Finally, we fix only one point here on the top. Let's call it pink. And we only pin this point so that the entire structure will not have a rigid body motion moving up or moving to the right. That may cause a singularity in your solution. And we only fix one point to minimize the effects for the boundary condition, from the boundary condition. So here we use pin here. When everything is set, now we can apply the load. First, we have an inner pressure, and your load must be applied to the step. And first, we have an inner pressure. Choose the one, and the inner surface is purple. And the pressure magnitude, first, our testing case, the pressure magnitude is 1 psi. And now we need to apply the shell edge loading, simulating the longitudinal stress. And this should be a shell edge loading applied on this edge. And the value for it should be 5. But the shell edge loading, if you choose traction direction as normal, then it's always following the compressional direction. So which means pointing to the negative Y direction. but we want it to be tension. That's why we need to put -5 here. And traction is defined per unit undeformed length. So it looks like this. Tension here and pressure inside the surface. Once you're done, you can do the mesh. So first thing is we need to choose the element type. Right now it's a S4R, so it's a reduced integration shell element. And we don't need a reduced integration. And then the control of mesh, we change it from free to structured so that it's more uniform. Because it's a static problem, you don't need to find for that, but basically you can do 0.25, and then now we can draw the mesh. If you want it to be finer, like I feel it's not as fine as what I want, put a 0.2 here, delete the mesh, and do the mesh again. Now, in the job, create our case or testing, or let's directly say case 1. So we don't need to do any changes here, and then we can submit our results. From the monitor, we can see what's happening. If you have any warnings or errors, it helps you a lot for these kind of simulations. So remember that we enter a section of 5, 8, 12, or whatever, but we only have one layer. That's why it has this warning. It's fine here. It's totally fine. It will be removed automatically, but later it helps us a lot. We don't need to reset these things. So I'll show you later. Now, if you see the result, I don't want the mesh size here, so I go to option, common is free, edge free. Choose the contour plot. You can see everything is pretty uniform except this corner, which we set additional constraint to it. That's why it has a small stress concentration, but it doesn't vary a lot. So to check the stresses, and we want S1 direction, which is longitudinal direction, we can see that all of them are pretty close to 50, which is the same as our theoretical prediction. If you see S2, which is following the hoop stress direction, it's pretty close to 100, which is also the same as our theoretical prediction. So we would say this is a very good guess or very good simulation for a thin wall pressure cases. So we don't need to change load anymore, just need to change a value. Now we can start our real task, which is to design the composite layout until it is smaller than 1.5, until the longitudinal direction for each layer is smaller than 1.5%. So go back to your property. Now we need to have a composite here. So for composite, you need to do elastic, and then this type change it to lambda, and we can directly type in these things. 17 mega psi, so don't forget the units. This should be 0.9 psi, 0.37 for Poisson's ratio, 0.75 psi, and 0.75 psi and 0.5 psi, mega psi. Since composite is always is pretty ductile, so usually you don't have plastics deformation for it. It's pretty elastic. Now go to the composite layout manager. We can directly edit it. And we need 4 layers, but we can hide the aluminum layer, and then we need 4 layers after that. So we do plies after, or you can use Control plus A here. So in total, you have 4 layers. Let's call it 30 degrees. And let's call it degrees minus 30. And let's call it degrees 90. The first layer of degree 90. The second layer of degree 90. Following the sequence here, from inner to outer, you have 30, minus 30, 90, and 90. And the region, we can select all of them and let me redo it again. Degree 30, degree minus 30, degree 90 of 1, degree 90 of 2. And the region, you can select all of them, right click, edit region, and select the shell you have. And then material, select all of them and change it to composite. Thickness, select all of them, change it to 0.009. So, and layout is the same. We can follow in this coordinate system, but the angle should be 30. This is in degrees. So minus 30, 90, 90. You can check the angle. This should be 30. You see from the longitudinal stress, the one direction is 90 degrees away from that, minus 90, minus 30 and 90, 90. All of them has an integration point of 3. Let's just do 4 plies and see what happens. Oh, by the way, we don't need aluminum anyway. So this will be your ply. You can also plot your ply here by ply stack plot. You should be able to see the ply stack plot there. And then we don't need to change anything here. The loading now, it should be 6,000 psi for the inner pressure. And the longitudinal stress should be 5 times that, so it should be 30,000. Everything stays the same. Now we can run the job. So once it's completed, now you can see that start from 14, we don't have the value for it. That means we have 2, 5, 8, and 10. 2, 5, 8, and 11. That means we have 4 layers. Now if you see the results, well, we want to show in the undeformed shape. And now we want to check the strain in fiber direction. So we use strain, and remember our fiber direction is one direction. Since our material property fiber direction are defined to be 1, and this is the E1. And to see each ply, we go to the result section points here, plies. You have all your plies. First, we have negative 30 degrees, which is your first ply. You can see here. And almost, well, this, you always have a stress concentration. You don't need to focus on this one. The one you need to focus is the entire these domains is like 11.2, around 11.2 percent. And this one is around 11.8%. This two layers should be the largest, 90 degree and 90 degree 2 and 90 degree 1, because they are sustaining the hook stress, which is way larger than the longitudinal stress. And you can also see it here. This should be this color, which is almost 15%. So to reduce the stressing, to reduce the strain to 1.5%, now it's 15%. So we need to have, this is almost 15.3. So it's almost 11 times of the strain we want. So that means if you want to reduce the strain to 11 times smaller than that, you need to have at least 11 layers of your composite. So that's why here we need to copy and paste the same sequence, and we use n copies to need to do 10 more copies, so you have 11 times thickness compared to original one. Now you have 11 copies, and you don't need to change anything, just rerun the simulation. And once it's finished, you need to wait until it says completed. So now you can see the strain in one direction of the first ply. So this will be your first ply. This actually is your fifth ply. Don't forget of it. It sorts by the name, not the plied sequence. So if you see this now, all of them is almost green, which is 1%, around 1%. And you can check here. This is the fifth ply, which has the same direction as the first ply, but it should be smaller than the first ply. So, which means we only need to check the first 4 plies, whether they are smaller than the desired strain criteria. If they are okay, then we don't need to check the rest. So as I said previously, we need to check the 90 degrees. So this 90 degrees, most of them are in green, which is less than 1.5%. So yellow is 1.47%. So we check the other 90 degrees. It's also smaller than 1.5%. So this is what we want. This is the desired stress state, desired layers. If it is a little bit larger than what you want, you can also add 4 more layers just to reduce the stress. So we have completed our first task, which is designing the layout for composite to satisfy the failure criterion. Now our second one is to simulate the actual pressure vessel. Usually we will have metals in the very inner layer for that. Since the composite itself can have a leak because it's brutal. So usually we need to add metal layers for the very inner layer. And here we just use aluminum for that. And by aluminum, we use a bilinear plastic model. So this bilinear plastic model, this is the stress and strain curve come from the experiment. And because we are LT tension, we choose the third one. And bilinear model means we can consider that as two linear lines. And the 2 points we're going to introduce here is first the yielding point where you have 0 plastic strain is 38 KSI. And the second yielding stress is 48. And here you will have 4.0042 as your plastic strain. Sorry, I think, let me think of it. I think this value is not correct. This value should be when you have 3.8, you have around 0.0038 plastic strain. So when it reaches 8, the elastic strain should be 0.008. Sorry, when it reaches the stress of 48, the elastic strain should be 0.0048. And the total strain according to the graph is around 8. So the plastic strain should be 0.008 minus 0.0038. So this should be 32. So let's go to the property and edit our element first. The Young's modulus and Poisson's ratio, if you according to the graph, it should be the same. So we just need to add the plasticity model to it. So we have 2 points to simulate the bilinear model. So add a row after. So the yielding stress, first one is 38 KSI. Oh, sorry, 38 E3 KSI. Second one is 48 E3. Plastic strain. Notice that this is plastic strain, it's not total strain. So for 38, it should be 0. For 48, as I mentioned before, it should be 0.0032. 0.0032. Now, if you go to the Composite Layout Manager, it's pretty convenient. We can enable our original aluminum layer, but now, and it is layer 1, so the most inner layer, and the thickness should be 0.04. And degrees, let's just use 0 degrees, so it's longitudinal direction. And however, the loading stress now is simulating the actual weight. So when we manufacturing the pipe, we add a preload of 5,000 psi to it. And under this pressure, usually we will introduce a plasticity inside the aluminum. And this plasticity, when you release the stress, it will result in a compressional residual stress in your whole structure, and that can greatly improve your cyclic loading behavior, or let's say fatigue behavior. fatigue life or something. And finally, let's recheck the reload. After we reload with the operational pressure of 4,000 psi, it should be smaller than this 5,000 psi, which is a little bit higher than the operational pressure. So let's go to the step. We have three step here. First, we rename this one as preload. And then we have another release one. It's called release. No need to change anything. And lastly, we have reload. So the boundary, the loading condition for this three step is different. And make sure that this is propagated through the release and reload. So we will calculate the string for each state. Now go to the loading step. These two are created at the preload stage, so it will introduce +6 string. And then we deactivate the release stress, means these two are released. These two stress are released. And now we create reload pressure. Select the surface and the purple one, and the reload magnitude should be 4,000 psi. And don't forget to change this to 5,000 psi. And change this to 5 times that, so it's 25,000. Now we can create a reload longitudinal stress, which is a shell edge loading applied to this edge. And it should be 4,000 times 5, so minus 20,000. Undeformed length. It should be applied to the reload, not the preload. So everything looks good now. So the first step, we're going to apply the preload. Second step, we're going to release the stress. Third step, we're going to reload the pressure, inner pressure. Make sure to check your output to include the plastic strain here, so we can see whether the structure has reaches the plastic strain, a plastic stress loading. So finally, we can directly run a job and create case 2 here. You see how does it look like, but let's see the stack sequence here. Choose that one. You can see that the very inner layer is aluminum, and then you have 44 layers above it. So the layout should be like this. And finish the first one. And the red one is your fiber direction, or one local definition for your one direction. So our definition for aluminum for one direction is pointing to the longitudinal direction, one, which means your reference direction. Okay, it's completed now. You can see here. So we mainly check the plastic string. So use this tool to select the stage. The first stage is preload. After preload, you can see that entire plane you have some plastic string here, and this plastic string will result in a residual stress when you release it. So we can see the stress. We choose S22, which is a hoop stress. Of course, when you have increase a layer, the stress will decrease because the thickness increases. But then when you go to the release stage and click one more after released, you can see the entire hoop stress state in the plate is in compression. And then after reload again, you can see is mostly between 5.25 to 5.28. Definitely if you see the aluminum layer, you can see the aluminum layer here. So at the preload region is like 5.17 to 5.15 or something. But then finally at the reload region, after you have a reload, you will have almost the same as the preload region. So 5.28, 5.19. It's almost the same. So this is how you do an analysis for your thin wall pressure loading. And I hope that this can help you. So now I'll hand the speech to Professor Go Yao again.
Thank you, Lifu, for going through that. In the example that Lifu discussed, what we can see there is that the analysis of the liner, yeah, it did go into compression after autofritage. So basically, you took it to a pressure level such that the liner gets plasticized. Then, when you remove the pressure, you saw how the liner became in compression because the composite wants to push it back to the original deformed configuration because the overwrap is not, it's a linear material typically, while the liner is plastically deformed. So liner wants to stay where it is. The composite wants to push it down. It doesn't happen. However, when we go to the tension cycle, what you can see there is that we didn't, the stresses are similar to the first step around when we're first increasing the pressure. And part of the reason is because we did not choose a material that's quite elastic plastic. And if there's more plasticity, then perhaps we will see those effects. And the other thing is in the modeling technique we use are shell elements. We didn't focus on the dome, but the idea of modeling the dome is not as difficult. The ply angles vary across the dome and the thickness as well. So with that said, I hope you enjoyed this presentation and that you learned something valuable in when you ever encountered having to design a composite overwrap pressure vessel.